Welcome, everyone. On behalf of the Southern Alliance for Clean Energy, I'd like to thank you for joining today's webinar about how climate change is affecting hurricanes. My name is Susan Glickman, and I'm the Florida Director of Southern Alliance for Clean Energy. Can everybody hear me all well? I've
Yes.
got, if you have any questions, I'm going to go through a few housekeeping things, and if you have any questions in the meantime, or can't hear, we have a chat box. But for those of you not familiar with Southern Alliance for Clean Energy, we're a regional membership organization. We promote responsible energy choices to ensure clean and safe and healthy communities throughout the Southeast. And we would like to acknowledge our members on this call and encourage those of you who are not members to please join today. And for ways in which you can get involved and become a member, just visit our website at cleanenergy.org. And I just want to take a quick moment to review the basic functions of the Zoom platform. I think we're all getting used to doing Zoom calls these days. It's along the bottom of your screen. To ensure sound quality, all of the attendee lines are muted throughout the presentation. If you have any kind of trouble hearing or seeing the slides, just click that chat button and you can direct questions to panelists or even to other attendees. Just type in your problem and then we can help you troubleshoot then. So we've also saved time at the end of the presentation to answer questions and have discussion. And so to ask a question, click on the Q&A button along the bottom of your screen as well. And we'll work to get to as many questions as we can. So you see Q&A, it's on the bottom of your screen to the right. And lastly, we are recording this webinar and it's going to be posted on our YouTube channel so you can share it with other people as well. So next slide. Before I introduce and then turn it over to Dr. Timothy Hall, I just wanted to set the stage for a moment about what we're about to hear, because the ways that climate change is affecting hurricanes may bring more, and it's a term I'm hearing more and more frequently, cascading effects. It's really a chain sequence of interconnected failures that, like a toppling dominoes, really impact these catastrophic events. The current set of really challenging societal issues that are before us, the climate crisis, the COVID-19 pandemic, and also the income and racial inequality that's being further exacerbated and exposed, where the most vulnerable among us are really seeing these cascading impacts. And for example, when a stronger hurricane hits, and that's what we're going to hear about today, and evacuations become necessary, it's those frontline communities with few resources that may not be able to get out of harm's way. And they suffer, and we all suffer to some extent, with the loss of tourism and jobs and depleted tax revenues. So as we listen to Dr. Hall, please keep in mind that sea level rise is already underway. So it's the more intense and slower moving storms on top of the already higher sea level rise. Again, these are these cascading impacts that I was referring to. What happens to the glaciers and the ice sheets of Antarctica and Greenland directly determines what our sea level rise and our shorelines are going to be all over the world. So I would be remiss if I did not underscore how extremely important it is to do everything possible to slow the global warming, which means we have to dramatically reduce carbon dioxide and other greenhouse gas emissions. So joining us today, Dr. Timothy Hall, thank you so much for being here and taking the time. Dr. Hall is a senior research scientist at NASA's Goddard Institute for Space Studies in New York City. He's an adjunct professor of applied physics at Columbia University. His research addresses extreme weather hazard and its variation with climate, and he has a particular focus on tropical cyclones. He has over 60 peer-reviewed publications and was a lead author on the 4th National Climate Assessment's 2017 Climate Science Special Report. As part of his research, Dr. Hall developed the NASHM, the North Atlantic Stochastic Hurricane Model, which he uses to address questions such as the climate evolution of hurricane landfall rates, where he assists private sector stakeholders in hurricane risk analysis, which is so important and often helps to set our insurance rates and so forth. Dr. Hall has also built models for tropical cyclones and other ocean basins and winter storms over North America. And in addition to his position at NASA, he serves as a meteorologist for the Florida Hurricane Catastrophe Fund and has worked as a consultant for several modeling companies, reinsurers, investors, and he holds a PhD in physics from Cornell. So now with that, I will turn it over to you, Dr. Hall.
Hi, everyone. Thank you so much, Susan, for inviting me. Susan Glickman and the Alliance for Clean Energy. And thank you, everyone, for coming. I hope everyone is well and healthy and safe in these difficult times. And trying to share my screen here. Susan, I think you have to release your screen so I can share. Thank you. That helps. Share screen so I can get to my slides. Share, go to full screen. Okay. So yes, these are difficult times, and I'm going to talk about one aspect of these difficult times. And I'm not an economist, but of course, this is related to things that are going on in the country aside from climate change, such as the coronavirus pandemic, and as well as civil unrest around the country related to racial inequality. So these things, although they have different causes, they aren't necessarily causally linked. They can have related ramifications that can exacerbate each other. So I'll touch on that at the end. But mostly today, I'm going to talk about the climate and the physics and the meteorology of hurricanes. So the title of my talk is Changing U.S. Hurricane Hazard. And that's me at the bottom, Tim Hall. I'm a staff scientist at NASA's Goddard Institute for Space Studies in New York. It would be remiss if I didn't note that we have just entered the 2020 hurricane season. So I should talk for a few minutes about what that means in the short term, this particular season. There are a couple of factors that can either make a hurricane season more active or less active. I'm not talking about long-range climate change now. I'm talking about UD or natural variability. I'll get to climate change in a moment, but just let's talk about the short-term view. And this particular season is believed to be and has forecast to be very active. And that's because two of the main factors that have an influence on the hurricane season's activity are the ocean heat in the Atlantic. I'm talking about the Atlantic hurricane activity at this point, and also the state of El Nino, which is one of the major natural variations in climate globally. When the Atlantic is warm, you can get an active hurricane season. And when El Nino is not present or roughly neutral, that also exacerbates and gives you a higher chance for an active hurricane season. Both of these factors are in place right now. If you look at that map on the left, that's the sea surface temperature anomaly, the amount above or below the average state for this time of year. And the warm colors are above average and the cool colors are below average. So you can see in the part of the Atlantic that matters for forming hurricanes, that's the tropical North Atlantic. We're above average by a considerable amount. But now actually in El Nino is roughly the state of the ocean temperature in the tropical Pacific. And you can see that band of blue along the equator or just above the equator in the Pacific. And that indicates that El Nino is not active. And that also means a higher Atlantic hurricane season. So both of those factors are pushing towards an active season. It's a little early in the season. In fact, officially it only started on June 1st, but actually it turns out we've already had 3 tropical cyclones. Luckily, they didn't reach hurricane status. We've got one right now called Cristobal that's spinning in the southern Gulf of Mexico and projected to head north, possibly with the US landfall, though maybe not as a hurricane. And we have Bertha and Arthur before then. I just thought it would be fun to show you what 3 tropical cyclones already at this date in the season looks like compared to years past. And that's that figure on the left. You can see along the x-axis the day of the year. And then on the y-axis is the number of tropical cyclones that have formed, not necessarily reaching hurricane status, but just tropical cyclone, tropical storm status at least. And the dark blue line is the average over many years past. So by the end of the season, you on average get around 12 tropical cyclones forming. And it typically, you don't get one or so until halfway through the year. Um, and you can see I've marked in red symbols Arthur, Bertha, and Cristobal, 1, 2, and 3. That's what we've had so far. And that light blue region is the most we've ever seen and the least we've ever seen down below by that time of year. So right now we're ticking along at the most we've ever seen. But it's pretty early in the season. And I should say that unlike weather forecasting, like a week or two out, and unlike long range climate projections, both of those things we have some skill at. There's an intermediate range, which is like predicting a year in advance or a season in advance or a year or two in advance, where the climate change signal doesn't quite pop out of the noise, but it's beyond our range for weather forecasting. That is a very difficult time frame to forecast, and seasonal forecasting falls in that time frame. So the bottom line is we don't have a lot of skill in our seasonal forecasts. In particular, we have essentially no skill in saying that, oh, we're sitting in April or May or something, and is a storm going to hit Miami in August? We have no skill at saying that. We have some skill at slight shifts in statements about chances for the overall activity of the Atlantic. So that's seasonal forecasting. And since we started the season just a couple of days ago, I'd be remiss if I didn't mention that. But our understanding of the relationship between climate and hurricane is not based on a particular season or a few seasons. It's based on a long-term view, both a theoretical and a modeling understanding, and also historical analysis over many decades of how climates and hurricanes interact with each other, how climate influences hurricane. And I like to actually rank these impacts by what we know for sure on the top, the arrow pointing out more certain, and what we know, which is interesting and possibly, hazardous, but we know with less certainty going down the list towards the bottom. So absolutely for sure, number one, and this is not even a climate issue, is that regardless of climate change, even if hurricanes weren't changing with climate, we've just got more population and infrastructure in harm's way. So that's a given. Number two is the first climate change point, and that is the fact that rising sea levels are one of the most robust projections of a changing climate, simply because warmer ocean water takes up more volume, so it rises. And in addition, we're getting a larger and larger component of that from melting ice sheets in Antarctica and Greenland. And that means that even if hurricane statistics weren't changing, you start with a higher baseline, you're going to drive that storm surge deeper inland. So, very robust projection is that that the greater storm surge and storm surge is increasing, and there'll be more hazard from that going forward. And almost with as much certainty, number three is that more intense rain events. And this isn't a statement just about hurricanes, any kind of extreme weather event like summertime convective activity. You basically have more warm air can hold more water in the vapor form. So when the meteorological conditions are right, like they are in a hurricane, you've got more water vapor to form into rain and precipitate on land. Now, 4 is very interesting. It's received a lot of attention lately, and there's a pretty good consensus in the scientific community that studies hurricanes and climate, and that is that hurricane intensity is increasing due to mostly to the warming of oceans, although there are a lot of meteorological details that go in there. And then 5 is a topic that's a lot less certain, and we still have a lot of T's to cross and I's to dot, so to speak, but I'm very interested in it, and that's changing hurricane tracks. How is the propagation of the storm changing, which obviously has huge implications for coastal hazard. And there's some evidence now that the storm tracks are slowing down and becoming more likely to stall, which is not a good thing if they stall over your coastal region. And finally, number 6, you might think everything about hurricanes is changing in a bad way, but actually over the globe, there's some reason to believe that fewer tropical cyclones overall will form. But the problem is that the ones that do form have a greater chance of reaching the most intense levels. So I'm going to talk about a few of those things, by no means all of them. Basically, I'm going to talk about intensity, and I'm going to talk about track changes and stalling. Mostly because that's what I'm interested in, and it's just too much to talk about everything. So intensity. Warmer oceans and the changing vertical profile in the atmosphere, the average vertical profile of moisture and temperature, come together to form situations that allow for hurricanes to become more intense. And that's seen in both climate change model projections, and now recently it's seen pretty robustly in the historic record. And on the left-hand side of this slide, I've got a map of climate change projections to the end of the 21st century about changes in the maximum intensity that a hurricane can reach. This is this theoretical concept called the potential intensity. It's basically like an upper speed limit for hurricane intensity given the environment they propagate in. And that speed limit is increasing. Any given hurricane can have an intensity sort of from 0 up to that speed limit, but if the speed limit increases, the distribution gets stretched out and you've got greater chance to get to the upper part of that distribution. And this map here I'm showing you, red is regions of the planet where that speed limit, the potential intensity, is projected to increase. And you can see it's over much of the planet, especially near regions that have heavy population. Um, okay, so those are climate model projections. What's actually happened historically? Well, that's what I'm showing on the right here. This is a recent paper by my colleague Jim Cosson. And Jim's actually put together a carefully homogenized set of historical observations, trying to remove any kind of observational biases and putting together a homogenized record over the satellite era. And what he sees when he does that is that a greater fraction of hurricanes are reaching major hurricane status. That's category 3 or higher. And you can see that in this trend here. It's noisy for sure from 1980 to the current year, or close to it. You can see that it goes up and down and up and down, but there's a clear unmistakable trend, and you throw any statistical tests at it and it's robust. So both from model projections into the future, we see that hurricanes will be getting more intense, and from the historical record, we see that more hurricanes are reaching the most intense levels. And just as a reminder, it's really the handful of historical storms that have reached the highest intensity categories that have done the vast amount of damage, say, on the US. Because the damage of a hurricane it doesn't vary linearly with its intensity. In fact, it varies probably as the wind speed to the 3rd power. So twice the wind speed means 2 times 2 times 2, 8 times the potential devastation. So really the vast majority of, say, insured losses on the US over the historic period are just due to a small number of storms. So just small changes in intensity can have big impact. But these are statements. These are either global statements or statements about, at least over the entire ocean basin. But actually, when it comes down to hurricane hazard where people live, other factors in addition come into play, and that's what I'm going to talk about in this slide. This is summarized in the paper that I just submitted a couple of months ago. And it really, I want to make the point that it's not only that storms are getting more intense, but other things are changing too that matter for regional hazard. For instance, where do the storms form in the ocean? And once they form, how do they propagate? And if those things are changing as well, those signals could actually swamp the signal of increasing intensity. But in any way, all three of those things come together to structure the changes in the hurricane hazard at a regional basis. So what I'm showing here, this is a complicated figure, but I'm gonna walk you through it. In the top, in the panel that has a 4.8 in it in the top center, that's actually into the 2030s. So roughly say up to 20 years from now, it's showing where there will be increases in the regions of the ocean, the Atlantic, where storms form. And that's basically in that big red spot off the western coast of Africa. So more of the storms will be forming there compared to other regions. And then next to that, those blue and red lines, those are average hurricane tracks. And the red is what I'm projecting in the future into the 2030s, and the blue is the historical baseline. And you can see there's a somewhat subtle but statistically significant shift eastward. So the tracks, they approach North America, but they curve away a little bit at a point further eastward than they would have in the past. And that has like complex implications for US regional hazard. And I'm going to get to those implications in a second. But first, I want to point your eyes down to the lower left hand of this panel, of this slide. In the black, I'm showing the fraction, the top black curve that says fraction North Atlantic TCs making US landfall. So this is the fraction of all storms that form in the North Atlantic, the fraction of them that actually hit the US. So historically, it was around 28%. But sometime in the late 1980s, especially when sea surface temperature in the North Atlantic started to take off and increase, dramatically, that fraction has declined, and now it sits around closer to 22% or so. So that would seem to be good, right? Because there may be more storms forming, but they're less likely to hit the US. On the other hand, the red line is the fraction of storms that form that reach major hurricane status. So over a historical period, that was around, 17, 18, 19%. But that actually around the same time in the 1980s started to increase. And so now it sits around 25, 26%. Those two things are kind of like canceling each other out. There are fewer storms that hit the US, but the ones that do are more likely to be in high intensity. And so the very bottom line there is the fraction of storms that form in the North Atlantic that make US landfall as a major hurricane. And that's sitting around 4% or so. And that actually is roughly flat because those two other effects are canceling out. So what about regional impacts on the US? That's the picture on the lower right. The changing, if storms form a bit further eastward, like there's a tendency for them to form now off the coast of West Africa, those storms are somewhat less likely to make US landfall. And also if the storms recurve before they penetrate far enough west to make US landfall, that reduces the odds for US landfall. But storms that are anyway enter into, say, the Gulf states, the shift eastward in their tracks just means that you get kind of storms that would otherwise make landfall, say, in Louisiana and eastern Texas, now make landfall in the northern Gulf of the Florida panhandles. These are a lot of complicated things are coming together here. But the picture on the bottom, red shows where it's going to be more likely to get category 4 or higher, category 4 or 5 hurricane activity in the 2030s. And blue shows regions where it's actually less likely. So in particular, I want you to focus on the fact that the Gulf Coast of Florida and the Florida Panhandle is actually a region where it's more likely. So this is a long-winded and complicated sort of slide that just, and the take-home message is really that a lot of things are changing simultaneously with climate concerning hurricane activity. And they can result, those things combined, result into a complex picture of regional hazard change. This is actually a further summary of those points. And this is also in this recent paper. What I'm showing here are the average rate of landfall for category 1 storms in the top panel, category 3 storms in the middle panel, and category 4 storms in the bottom panel for 4 US coastal regions, Galveston, Tampa, Miami, and Cape Hatteras. I just picked those because they kind of spanned the hurricane active region of the coastal US. And you can see, for example, if I say, look at the category 3 storms, those are major storms, major hurricanes that, so I'm sorry. So purple is the historical baseline. Light blue is the current period, the decade we just exited, and red are the 2030s. So in Galveston, you actually get a decline in hurricane activity there. And that's pretty much because the storms are shifting eastward away from the US coastline. Whereas in Tampa, you actually get an increase in activity. And that's because storms that otherwise would hit further west in the Gulf are now shifting somewhat eastward towards Florida, and that results in an increase. So again, this is indicative of this complex signal. And this is only in the US. I mean, if you went around to other regions, like say the Asian Pacific sector or Australia or the Indian Ocean, you would likewise see complex signals like this. Okay, so now I'm going to shift gears a little bit. I'm going to talk about another aspect of changing hurricane hazard. And this is something that my colleague Jim Costin and I worked on the last couple of years. And that is that there's some very interesting and somewhat alarming evidence that tropical cyclone tracks are slowing and becoming more prone to stalling. I've just shown on the top here 4 examples of recent tropical cyclones, 3 of them pretty infamous hurricanes: Harvey in 2017, Florence in 2018, Dorian in 2019. Also, somewhat lesser known tropical cyclone, unless you happen to live in that region of Texas, Imelda in 2019. All these storms, what these storms have in common, they all stalled. And that is that when they got near the coast, they slowed down. They spent a long time in a confined region, possibly wobbling around a bit, but not getting out of that region. And during that time, they dropped a lot of rain, not to mention whatever wind damage. And they caused flooding and some of the more intense ones, major wind damage. Harvey, obviously an infamous flooding event in 2017, Florence in North Carolina in 2018, Dorian last year on the Bahamas, and Imelda was a major flood event, although it wasn't a wind event, in Texas. So Jim Costin, my colleague, in 2018 wrote a paper that documented a decline in the rate at which storms propagate. I don't mean their intensity, not the circular component of their wind speed, but the rate at which the entire storm, moves across its ocean basin, not just in the Atlantic, but in other oceans as well. And that's what that figure on the left is showing. It's the translation speed in kilometers per hour as a function of year. So you can see there's a lot of noise. It's not a clean signal. Very few signals in climate change business are. But he's done some careful trend analysis on it, and there's a clear decline. So storms are slowing down. Subsequently, he and I got together, and we saw that that slowdown was mostly driven by an increased propensity for storms to actually stall. So it wasn't like all storms just slowed down a tiny bit. It was like a few storms were becoming more likely simply to stop dead in their tracks, and that was dragging down the average. And so we actually defined a stalling metric, and we could have defined it in many ways, but we chose to define it as a storm that spends at least 48 hours in a 200-kilometer radius circle. And we looked at these regions, these 200-kilometer regions along the US coastline, and we documented year by year what fraction were actually stalling according to that metric. And that's that figure on the bottom. So from roughly the late 1940s to the present day, there's a noisy but an increased propensity for storms to stall. This is a bit of meteorology here. I want to talk about, this has been somewhat, okay, this result has been somewhat controversial, and a lot of people have analyzed it very carefully to see whether there was some bias being introduced due to historical records changing during time, the measurement techniques changing over the years, and but so far it's stood those tests, it stood up to those tests. So it really is important to understand, to establish this signal, to understand what might be causing it. And we haven't totally figured this out perfectly well, but there's some pretty good suspects. And in order to understand one of the major suspects, you have to appreciate what actually causes a storm, a hurricane, to move. I mean, we know it's spinning because it's kind of a big thermal engine, but what causes the storm, the whole system en masse, to move across the ocean and say maybe hit North America? Well, to a good approximation, hurricanes they're almost like spinning corks that are carried along by a stream. The stream is the large scale wind patterns in the atmosphere. And to convince you of that, I've made this scatter plot, I call it, with all this big swarm of red points here. And in that scatter plot, I've got on the y-axis is the movement of the hurricane. And on the x-axis is the large scale east to west wind pattern in the tropical Atlantic. And you can see there's like, yeah, there's a lot of scatter, but there's definitely a correlation there. So in other words, hurricanes are responding to these large scale wind patterns. The second ingredient is that it's a very robust feature of climate models. When they do global warming simulations, they see a slowdown of the large scale wind patterns in the tropics, what we call the tropical circulation. Now, even though it's a robust figure across many climate models, the details of why that's happening in the models are still being debated. But it's definitely there, and it seems to be driven by climate change. And then the figure on the left, I'm just showing you, don't worry about the details of what's on the y-axis. It's basically complicated meteorological mumbo jumbo that measures the strength of the tropical large-scale wind patterns. And the blue bars, across most of that figure, or each bar is a different climate model doing a climate change simulation. And the vast majority of them indicate a reduction in those large-scale wind patterns. So taken together, climate change reduces the large-scale wind patterns. It is those wind patterns that drive the propagation of hurricanes. Hurricanes slow down, become more likely to stall. So to make this a little bit less theoretical and abstract, I thought I might show you a really awesome in the scary sense, video clip of Hurricane Dorian from 2019 doing a very dramatic stall at high intensity, Category 5 over the northern Bahamas. So let me start this. And here we go. There's Dorian heading westward at a normal clip. This is about an average rate of propagation for a hurricane. A couple of days go by. It's August 31st, and it's approaching the Bahamas, still about at that same rate. Now watch what happens. September 1, watch what happens right about now. It's Category 5. Stop. Category 5, Category 5, Category 5, spinning and spinning and spinning over the northern Bahamas for over 48 hours, and all the devastation that ensued from that before it finally heads off north along the US coast. And it's that kind of event that we are afraid we see evidence of is becoming more common. Okay, I don't need to see it again. There we go. Now, another storm that also stalled. Now I'm going back a couple of years to 2017. And this time I'm going to talk about one of the major impacts of a stalling storm. This is Harvey in 2017. And when a storm stalls, this is kind of commonsensical. When a storm stalls just off the coast, it's sitting there spinning for a long period of time. It's drawing up warm seawater from the waters it's sitting over, and it's converting that into energy that drives the storm. And in addition, eventually that water then becomes rain, that water vapor becomes rain, and it can drop that on, population centers near the coast. It's just, and Harvey is this sort of archetypical, the poster child example of this. So this is a little video clip of Harvey. It actually weakened as it crossed the Yucatan Peninsula. Now it strengthens dramatically. Right now it's reaching Cat 5. Makes landfall. Look at it wobble back and forth. But at the same time, you can see the red spots are where it's raining. Rain is accumulating over Houston until you get like record-setting total rain, until it spins off into the central US. And, it's kind of common sense that if a storm just sits there stalled over the coast, it basically becomes a conveyor belt carrying warm nearby coastal waters and dumping it as rain on the coastal communities. Although when Jim and I wrote this paper, it took the reviewers some convincing of this, so we added this figure to the paper. In the top left, I've got the number of hours that a storm sits over the coast. This is based on a whole bunch of storms historically. The number of hours it sits in a confined region from 0 up to 80 hours. 80 is an extreme stall. And then on the y-axis are the cubic kilometers. How's that for a unit of rainfall? A cubic kilometer of water being dumped on that region. And you can see the more hours you sit in one place, the more cubic kilometers of water get dumped on a region. And I think the cubic kilometer is a pretty awesome unit for accumulated rainfall. It really illustrates the hazard well. And that the cartoon on the right captures it kind of graphically on a gut level. You can see the amount of rain that fell on Houston from Hurricane Harvey, if you put it into just a big blob, is more than 2 miles, a cube more than 2 miles on the side. And there's downtown Houston sitting underneath it. So imagine what happens when you just drop that big cube on the city. So I'll conclude now, and I'll just say that I touched on only a few aspects of hurricane hazard changes in a warming climate. I talked about increased intensity. There's good evidence for that, especially when you look at it in terms of the fraction of storms that reach the most intense levels. We see that both in climate model projections, but also now in the historical record. But that's not enough to figure out what are the impacts on the local regional basis. You also have to look at changing hurricane tracks. And we see some evidence that tracks are changing, which actually may ameliorate some of the impacts on the US, although the regional variations, but also there's more stalling, which makes a storm more hazardous. There are two aspects I didn't talk about because I don't want to go on for hours and hours, but two of the aspects I didn't talk about are really the most robust. And that is that the issue of increased sea level rise just means automatically that you have a greater storm surge hazard, and also increased population and infrastructure in harm's way. And on that last point, let me circle back to a point that Susan Glickman made in the introduction, and that is population and infrastructure. Yes, we have more of it in harm's way. Now you might say, well, we also have better forecasts and therefore better evacuation procedures. We hope that's true, and it is to some extent. We have more resilient structures. There are more stringent building codes in several states that are in harm's way. It's hard to say to what extent they're enforced, but they exist on the books at least. But during a pandemic or any other simultaneous catastrophe, say a major earthquake or something else that we might be subject to, related or not to climate change, where do people go? You know, I mean, during a pandemic, people are trying to isolate in their homes. We're going to send them all into the Superdome in New Orleans, like we did for Katrina in 2005. And do states and the federal government, for that matter, have the resources to respond to simultaneous catastrophes? So with that, I'll leave it, and thank you for having me, and entertain any questions.
Wow, Tim, that was a big wow. I see that ice cube above Houston. I live in the Tampa Bay area, and I am literally across the street from the Gulf of Mexico. I'm a Florida native, so I've been through a few hurricanes. So before we sort of get to questions, there's somebody really amazing that is on the call with us, and that's my friend John Morales, who's the most beloved and longest tenured broadcast meteorologist in South Florida at NBC. He's been through Andrew, Irene, Katrina, Wilma, and Irma. So John and Tim do know each other. So John, I just thought if you would, just say hello real quick if you had a comment or a question in particular for Tim.
Sure. I assume you can hear me.
Yes. Yeah, good to hear you. I remember meeting a couple of years ago with the Florida Pro team.
That's right, Tim. We have met, and I've got a question for you. First of all, I mean, great presentation. What is causing the hurricanes to recurve earlier? I mean, is it the quote unquote wavier jet stream, potentially driven by the rapid warming of the Arctic? And if so, then we would presume that trend would continue. Of course, that also plays into the stalling aspect that you just covered. Or, is this a shorter type of natural cycle, AMO related, NAO related. And I know I'm talking a lot of meteorological mumbo jumbo, but I'm sure you can unflesh that or flesh it out for the folks on the call.
Yeah, so I mean, the simple answer is we don't know for sure, but that's always a scientist's cop out. You mentioned it's not the NAO. I mean, that's essentially a weather signal. But you mentioned that the less stable, more meandering jet stream, that may have an impact on stalling in mid-latitudes, and that's for the other listeners, there is some evidence that as the Arctic Ocean is exposed due to increasing sea ice melt, that makes the Arctic regions warm more rapidly. That means less of a difference in temperature between the tropics and the Arctic. That means that the jet stream, which is driven by that difference, is weaker and more prone to meandering. And possibly you could get storms, hurricanes that reach the middle latitude regions, say, New York latitude or something like that, are more prone to actually doing a strange meander. I mean, Hurricane Sandy was actually a poster child for that type of thing. But in addition to that, John, this thing I mentioned, that the Hadley circulation, which is the dominant mode of air patterns in the tropics, appears to be slowing down. That's a very robust signal from climate change models. So that, we believe, is driving. I mean, that's our working hypothesis, that is driving the slowdown in the hurricane tracks and making them more prone to stall in the regions, the dominant region of active hurricane, which is in the subtropics, or up to say 30 degrees, 35 degrees north.
Okay. Just to follow up, how about the recurvature though?
Yeah, the recurvature is interesting, and we don't really know for sure, but it's possible that a natural mode of variability, which is called the North Atlantic Meridional mode. I mean, not the AMO. It's another. The AMO is a tough one because the AMO doesn't have. It's not even clear it is a natural mode of variability. But there are natural modes of variability that shift eastward and westward the subtropical pressure high in the Atlantic, and that a warming climate may be hitting that mode and causing it to shift into one state more likely versus the other, which moves that pressure high region a bit further eastward, and the storms sort of curve up the side of that pressure region. So if that high pressure region is not reaching the North American continent, the storms kind of are more likely to slip along and then recurve back eastward when they get into the mid-latitude circulation before they make North American landfall. But there are a lot of things we don't understand about that.
Thank you, Tim.
Great. So I'm going to read a question from Bill Bray, who is on here. Give me a minute. After Hurricane Harvey, we in Houston heard that 15 to 39% of the rain was due to a warm Gulf of Mexico. So 2 questions. Do you have any guidance on what numbers we should be quoting for this percentage of increased rainfall? And then number 2, do the first amounts of rain cause no damage, but the last few percent in these catastrophic events cause a huge and disproportionate amount of the damage? Do you have any comment or resources that they can quote on the amount of damage due to the warmer Gulf and these additional rainfalls?
Okay, on the first question about, I think the question is about what we call in the business attribution. And that is, you see a big event, whether it's rain or wind, and we try to ask the question, what fraction of that event can we attribute to human-induced climate change? And it's a new field. It's a very exciting field. It's an important field. It's also quite difficult. It basically amounts to simulating 2 worlds. One, the historical world where the event happened, and the other, a kind of contrafactual world that didn't have a warming climate. There weren't, say, carbon dioxide and other greenhouse gas emissions. And we do that multiple times, and we look at the difference in the distributions of events similar to the one we're interested in. Because this involves using climate models, and because climate models vary in their details, that's why we don't have a single projection for warming climate. We have a range of projections. That same type of range is impactful in this attribution exercise. So different people did the attribution using different models to Hurricane Harvey, and they came up with different estimates. So that range indicates the range of estimates that come up. So it's hard to say, give you a single answer, but if you need a quick one because you're talking to stakeholders, so you're trying to do climate communications and you only have a finite amount of time and finite amount of attention being paid, take something in the middle. And you can say roughly, 25%. And then you can back it up with, the literature that shows a range of values that include 25%. I'm sorry, it's not as if we know what the single answer is and we're kind of,
Right.
we're trying to mask it in a range. The range really indicates all the various points of uncertainty and estimates that go into that analysis.
Well, it's really the nature of science, right? It's
Yeah.
ever changing. Does the change in climate affect how far inland the storms may go? Or maybe larger storms go further inland? Are they likely to receive a hit in Asheville, North Carolina, like 250 miles inland?
Sure. A more intense storm that makes landfall a higher intensity will, in general, reach points further inland before it completely attenuates. That's absolutely true. On the other hand, storms that slow down and stall more actually may not. So there could be two competing trends there. On the one hand, storms are more intense when they get to land, so they can propagate further inland before they attenuate. On the other hand, they're moving more slowly, and really what determines the attenuation is how long over the amount of time over land the storm spends. So if it's moving more slowly, it's attenuating before it reaches points further inland.
And are there any sort of predictors for where these intense hurricanes are going to stall?
No, not at the moment. The best we can say is that, over coastal regions at least, and most likely over the entire sort of hurricane active region of the North Atlantic, we're seeing an increased tendency to stall. We're not able to say, oh, it's most likely to stall over, Louisiana or North Carolina.
Yeah. Do you, how much warmer is the Gulf of Mexico now than say it was in 1950?
It's the Gulf of Mexico. I mean, it's probably, half a degree warmer Celsius.
Mm-hmm.
I don't have that number off the top of my head, but I mean, that would be a sort of a typical amount of warming.
And wasn't
you may doesn't sound like much, but actually, I do know that in the subtropical North Atlantic, the standard deviation, like the amount of year-to-year natural variation you'd expect in averaged over the hurricane season and over a big swath of area in the subtropical North Atlantic, the major spawning ground for hurricanes, on average, the standard deviation is only like 0.3 of a degree centigrade. So when you get like something that's 0.6 of a degree warmer, it may not sound like much, but that's 2 standard deviations above the long-term mean.
Right.
For a statistician, that's a lot.
So do you think that we'll see the day where there's a Category 6 hurricane and or even an adjustment from the beginning, the start and the end of the official hurricane season?
I get this question a lot, so great question. First of all, the way things are defined now, no, we'll never see the day that there's a Category 6 by definition, because Category 5 is everything above a certain point. So even if we got to, wind speeds, supersonic wind speeds, it'd still be called Category 5. So I think the question would be, is it worth defining a Category 6? And I don't really believe it is. And the reason I don't believe it is because they're twofold. One is we already have a system for rating hurricane intensity that, goes up arbitrarily high. And it's just called, say, kilometers per hour or miles per hour or meters per second, whichever unit system you prefer. So I mean, I don't really think like, what is the Safer-Simpson scale? You have Category 1, 2, 3, 4, 5. It's just a very crude wind speed measurement. We already have much finer wind speed measurements that don't top out. So, if there came to be a reason to talk about, like, to differentiate among storms that were in the Category 5, crude basis, well, we already have a way to differentiate them. We can just say miles per hour.
Right. So wasn't the large scale wind pattern that seen as Dorian was moving through the Atlantic, meaning the forecast should have predicted that stall to some degree?
Yeah. I mean, I can't remember exactly what the lead time, not in the very beginning of Dorian's track when it was still forming, but uh, um, within a couple of days, there was some evidence that it was going to stall, because typically stalls happen where there's a forecast change in direction. That's the most common situation for a stall. So, I mean, the forecast models all said that Dorian's path at some point was going to veer pretty sharply to the north. And it's in those situations where you're most likely to get a stall. And the reason is because what happens is that the large scale steering wind patterns, the winds that are blowing from east to west, that are pushing the storm to the west, they kind of collapse. So the forecast models can forecast that collapse, but and so they know something's going to change in the storm's path. But it actually, that's when it's the most difficult to figure out where it's going to go, because at that point there aren't these large scale winds driving it that are relatively easy to forecast. So you have to base your forecast on the very small scale dynamics of the storm itself, or very nearby slight fluctuations in winds that could either push this teetering top one way or the other. But it was forecast within a couple of days in advance that there would be this collapse in the steering winds, and the Dorian would change direction. But earlier on in the forecast, it was thought that maybe that would occur so that Dorian would sort of, head right up the spine of Florida, and instead it stalled and headed north, 100 miles just shy of that. That's a problem with forecasting these things, is that for a meteorologist, 100 miles over the entire span of the Atlantic, that's pretty good accuracy.
Right.
It did turn north. On the other hand, in terms of who's in harm's way, 100 miles is a world of difference.
On that note, Laura Cassells from the Florida Phoenix is asking if you could please describe how that phenomenon defined Hurricane Michael, as it sort of seems like it came up suddenly, stayed strong, and then really acted like a massive tornado, really unusual.
Yeah. Hurricane Michael was an example of what meteorologists call rapid intensification, which is exactly what it says it is. It crosses over quite suddenly into a region that's very warm and very little wind shear. Both those things can allow a storm to intensify. But then in addition, there's very complicated internal dynamics of the storm that are just right, that allow the storm to take advantage of those favorable large-scale conditions. And they're another situation that is more difficult to forecast than a storm that is, say, slowly increasing or slowly attenuating. But they're becoming increasingly important. There's some evidence that the increase in overall intensity of storms is actually due to an increased frequency in rapid intensifiers. And Hurricane Michael did that, somewhere, not shy of the Florida Panhandle. And then at the time it was called a Category 4, but it was later upgraded to a Category 5 based on forensic meteorology.
So we're being asked if you could provide, Tim, links in the notes, or maybe we can do it in the follow-up, on reports or studies that you've either done or know about on the incremental cost projections through some of your work with reinsurance companies due to this increased cyclone damage. Do you have some information we can share on that either now, or we can do it in the follow-up?
Yeah, that's a funny thing. Actually, if you look back over I'm sure I can try to find some links, but that's the short answer. But let me comment on that. If you look back over, the record, at least since Hurricane Andrew in '92, which really started the whole business of catastrophe modeling for hurricanes, and you look at how reinsurance rates, these are the insurers of the insurers, and they sort of drive from the top the economics of insurance. How do reinsurers set their premiums? They actually set them, for the most part, post facto, retroactively. which doesn't really make a lot of sense in some level. So basically, you know, they set them based on some combination of long-term outlook for the hazard plus some profit margin and whatever other business factors that come into effect. They set them, and then lo and behold, there's a massive event. And they got to pay claims to the insurers because the insurers have to pay claims to the homeowners. There's a massive event. Then the following season, they jack up their premiums, basically to, you know, to recoup their losses.
Right.
So the bottom line is that I don't think that there is a clear signal of reinsurance premiums responding to you know, increased science about the projected increase in the hazard. So I don't think that, you know, the person who asked the question is going to get a very satisfying answer.
So on our Hurricane Michael, and I think this may be our last question, maybe one more, from Alvin Peters, who's also up in the Panhandle. What is the mathematical relationship between warmer sea surface temperatures in the Gulf and the strength of Hurricane Michael? Is there really a 7% wind speed increase for every degree Fahrenheit or degree centigrade? And related, why did upper atmospheric wind shear do so little to diminish Hurricane Michael?
I think the 7% per degree, I think that doesn't refer to the storm's intensity. It refers to precipitation, rainfall. That's a basic physics called the Clausius-Clapeyron relationship that, you know, if you increase temperature by a degree Celsius, you get a 7% increase in the amount of water vapor that new warmer air can hold. And that water vapor is now available to precipitate if the conditions are right, like they are in a hurricane. So that's not actually a statement about wind speed, that's a statement about rainfall. Actually, for hurricanes, it's probably more than 7% because not only is there more vapor in water form, but that when the water vapor precipitates, that actually heats the atmosphere and then drives a more intense storm. So these things come together. You get more rain and more intensification of the storm, which then picks up more water from the ocean. But that 7% is the thermodynamics of air temperature and water vapor in the air at saturation. So then the second question I think was about what's the physics behind warmer ocean temperatures and hurricane strength. I mean, a good approximation, a hurricane is kind of like a big thermal engine. It's converting the thermal energy in the warm seawater at its bottom into kinetic energy of a rotating storm. And I don't know if it's time to get into the detailed meteorology, but as long as there's a difference between the temperature at the bottom of the storm and the temperature at the top, which is in the upper troposphere, what we call the outflow region, that temperature then, the warm air wants to rise, and then it spins as it starts to rise because the Earth is rotating. And the greater that temperature difference, the greater the storm strength you can drive.
Tim, yeah, you are amazing, a wealth of information. It's and I eat and breathe and sleep this, and it was just so much to learn. Thank you so much.
Well, I want to thank the opportunity.
Yeah, very good. Thanks again to everyone for joining us today and for all of your thoughtful questions. The presentation today has been recorded, and we're going to send you a link to that recording once it's been processed. And if you enjoyed today's presentation, consider joining Southern Alliance for Clean Energy so we can continue to work towards clean energy solutions for the Southeast, and visit cleanenergy.org for information on how to join and get more involved. So take care, everyone, and have a great week. Thanks.
Thank you.